Lovely. So I will switch on recording now. Lovely. So thank you so much. We're very happy to welcome Professor Turok to speak to this group. Professor Turok is the Higgs Chair in Theoretical Physics at the University of Edinburgh and one of the foremost, really, cosmologists in the UK, if not internationally, I think. So we're very happy to have you with us. Thanks, Professor Turok.
Well, thank you, Corinne. Thank you for inviting me. Thank you, everybody, for being here. I just wanted to say that my own family were refugees. I was born in South Africa, and my parents were active politically against the apartheid government, and unfortunately both went to jail. And then my father had to escape illegally from South Africa. And we went to East Africa and then eventually came to the UK, basically so that us three children could go to school here. So I was a refugee. I'm very much sympathetic to your situation. I think many of you have gone through much worse than I went through. And so I just wish you all strength in coping with your difficulties. I see Kingsley is connecting too. Let's just say welcome. Oh, and Jonas. Okay. We're getting more and more people. That's nice. So just a big welcome to Kingsley and Jonas. Thank you for joining us. And as I said to the others, feel free to unmute and just say hello or ask a question, interrupt me during the talk. It's also fine. Are either of you able to say hello, Kingsley or Yosef? Yosef?
So Jonas has also...
Hello, how are you?
Oh, hi, Jonas.
How are you?
Where are you, Jonas?
I'm in Bristol, but I'm from Eritrea.
Okay, welcome this evening.
Okay, thank you.
And Kingsley or Yosef, are you able to say hello?
Yeah, can you hear me?
Yes, very good.
Hello.
Nice to meet
Okay.
you. Where are you joining from?
Nice to meet you, Professor. I'm from Derby.
Derby. Okay.
Yeah,
Very warm welcome.
thank you.
Kingsley. I see Kingsley. Hi. Hi, Kingsley. Are you able to say hello? It seems the connection's not great. Okay, well let me begin. So what I'm going to, like I said, feel free to interrupt, please. It's much more fun if this becomes a discussion. And I will stop at various points in the talk also to allow you to ask questions. So what I'm going to talk about, the title of the talk is Secrets of the Universe. Actually, nothing I'm going to say is secret. And the research I do is not secret. But what has been amazing over the last couple of decades has been the extent to which we are understanding how the universe works. And I literally believe that the universe reveals itself to us. What we have to do is look carefully and logically and try to understand things, try to make sense of them. And the harder we try to do that, the more we learn. And we learn some extremely fundamental things, you know. We're not able to answer the most profound questions, like why are we here? Or what is our purpose? Science is not going to tell us that. But what science will do, I believe, is help us appreciate the miracle of our existence and the wonderful things which are all around us and which constantly teach us. I'm a physicist, so my specialty is understanding how things work. What are the rules by which matter and energy operate in the universe? And those rules are extremely strict. The laws of physics we know seem to be impossible to violate. They allow us to do certain things, but they also prevent us from doing many things which we might want to do. So the laws are very strict, much more strict than any laws written down by human beings. The laws of nature are really very rigorous and don't change. Okay, so let me start telling you about the secrets of the universe. I'm going to show my screen. Corinne, will you allow me to show my screen?
Sure, you are allowed to.
I am allowed. Okay, great. So I'm going to show some slides. And so this one just really sets the scene. It's a rather beautiful scene from the mountains in Spain, in the Pyrenees. And you see this beautiful house sitting in the mountains. And then in the distance, we see the Milky Way. That's our galaxy. And every point of light in the sky is a star. And there are about 100 billion stars in our galaxy. 1 billion is 1,000 million. So there are about 100,000 million stars in this structure here we see overhead in the Milky Way. So we live in our comfortable home, the Earth. But when we look out into the sky, we see a vast universe in front of us, much, much bigger than anything we're familiar with in everyday life. And we now believe that many of these stars on the sky are surrounded by planets, just like our sun is surrounded by Earth, Mars, Mercury, Venus, Jupiter. And some of these planets probably have conditions suitable for life, but the Earth is the most suitable planet we know of for life, and we're very lucky to be here. The theme of this talk is that the secrets of the universe may be hiding in plain sight. And what do I mean by that? I mean that if we look closely and carefully and pay due attention and respect to what we learn, we discover these fundamental secrets of nature, the laws which govern everything in existence. And I'll give you some examples in this talk. So let me also say I'm from South Africa, as I mentioned, and the story of the birth of mathematics and physics and astronomy is not usually told correctly. Mathematics and astronomy and physics were invented in Africa, not in Europe. And these are some of the oldest human artifacts representing that tradition. So you see here on the top left this stone where a geometrical pattern of equilateral triangles is drawn. This stone is about 80,000 years old and was found in a cave in southern Africa. And so our ancestors were clearly thinking about geometry a long time ago. These two structures are from southern Egypt. This on the top right is the first astronomical observatory several thousand years before Christ in southern Egypt near to the Sudan. And it's called Nabta Playa. And these pillars, we believe, were used to make observations and to record the positions of objects, astronomical objects on the sky. And then finally, I'm sure you all know about the giant pyramids in Egypt, which were literally the use of mathematics, a translation of mathematics into buildings and massive structures. And so these were the first such massive buildings created, again, well before Christ, about these ones about 2000 BC. So it's clear that mathematics and astronomy and science originated with human beings in Africa, I mean, as human beings themselves did, and then propagated outwards across the world. So let me begin with the sun, a very familiar object to us every day, very important to human life. And I want to tell you something about the sun, which maybe you didn't know before. The sun shines with a particular color of light, and here you see a beautiful, detailed observation of the sun. It's a very complex structure with magnetic fields and solar flares and so on, and it's all driven by nuclear energy, the energy of nuclear fusion. And we're now trying to make nuclear fusion reactors on Earth, but nature did it long before us, and that's how the sun works. But the point is, it has a particular color, which is yellowy, yellow, and to some extent orange. And we obviously live outside the sun. Okay, so we live outside this spherical body, which is very hot and radiating light outwards. We also live inside a similar structure, and here's the Big Bang. Okay, so here is the solar system in the middle of the picture. The sun is there, and the planets orbiting the sun, and Earth is one of these planets, the blue one. But if we look outwards, what we actually see is a hot surface which surrounds us, this red surface. And literally it's like a sun, but a sun which covers the whole sky. It's not as hot as the sun, we see on the sky. And the reason for that is that this red surface which surrounds us was a similar temperature to the sun, but a long time ago. And so a long time ago, and that is actually at a time of about 400,000 years, when the universe was only 400,000 years old, this surface here would be roughly the same temperature as the temperature of the sun. But then as the universe expanded, the light, the hot radiation emitted by the universe all around us, this red sphere which surrounds us, that light has been stretched and cooled. And so when we now receive it, and we're now able to map this hot radiation from the universe all around us, that light has now become radio waves, which we can measure using radio telescopes. So what we understand is that we live outside one hot surface, the sun, spherical surface, and we live inside another spherical surface, which is literally the surface, the hot surface of the Big Bang. And as we look outwards using light, what we are actually doing is seeing the universe as it was earlier and earlier and earlier in time. So we are now about 14 billion years after the Big Bang. This hot red surface, as I said, is about 400,000 years after the Big Bang. And the white circle in this picture is the Big Bang itself. And it's a little bit strange because in this picture, it appears that the white circle is the largest object we can see. But actually, as we go outwards, the universe and backwards in time, the universe was getting smaller and smaller. And in fact, this white circle was a point, a single point. Every point on this sphere is actually the same point. And so I'll show some other pictures later. But we live inside a Big Bang universe which mysteriously originated at a single point. Now, I mentioned that the radiation from the Big Bang is mapped by satellites, and there was a revolutionary advance in cosmology in 1992 when this satellite called COBE, the Cosmic Background Explorer, managed to map the whole sky in this radio waves, which we believe are the relic of the hot Big Bang itself. And what the picture shows here is the intensity of the light plotted against its frequency. So as you probably know, light of different colors has a different frequency or wavelength. And so, for example, the visible colors like yellow, red, green, blue, the visible colors differ in their wavelength or frequency. And radio waves are really just another form of light with even longer wavelength. So this curve here, which is plotted, the green curve, was the curve predicted by theory from around 1900. So that is, almost 100 years before, 92 years before the experiment. This green curve was predicted. It's called the Planck spectrum. It's the most fundamental spectrum in physics. And it is the spectrum predicted from a hot body. If you just take what's called a black body, so take a body which actually has no color, it's perfectly black, and heat it up. As you heat it up, it will glow with a certain color. The hotter it gets, it will go red, it'll go yellow, it'll eventually go white hot. And the spectrum it emits is this shape. The shape is this green curve. You'll notice the red crosses. These are the experimental data from the COBE satellite, and see how they match absolutely perfectly. Now, this Planck spectrum was invented in 1900 at the very moment where the idea of quantum mechanics, it is the spectrum which gave rise to the theory of quantum mechanics. And so what I like to say is that the whole universe is shining at us and telling us the fundamental law of quantum mechanics, namely this Planck spectrum. And it's amazing that, human beings anticipated this result just on the basis of what a hot body should look like. And when eventually the measurements were done, they agreed perfectly. So we could have learnt about quantum mechanics if only we had seen the spectrum of radiation from the Big Bang. By the way, the spectrum that nature produces is easily the best, the most perfect black body spectrum that anyone has ever seen. It's very difficult to make a perfectly black body with this spectrum in the laboratory. Of course, Planck got his clues from such experiments, but the natural one is by far the best. The solar spectrum, if I do the same for the sun, you see a similar curve here, and you can plot the shape of the curve as with different temperatures of the sun. So if the sun was at 3000 degrees Kelvin, 0 degrees Kelvin is absolute zero. That's minus 273 centigrade. But if the sun was 3000 degrees, this would be a shape of its spectrum. Because the sun is at about 5000 degrees, it fits with this blue shaped spectrum. And here it is compared with the experiment. But you see that the spectrum of the sun is much more messy than the spectrum of the universe. And secondly, in fact, even the spectrum of the sun is very hard to measure unless you go above the atmosphere. The Earth's atmosphere contaminates the solar spectrum. So you see this picture here, it says the standard extraterrestrial solar spectrum. This is what you see if you put a satellite above the Earth's atmosphere. You get this jagged curve here, which is kind of the Planck spectrum, but it's a bit more messy than the one from the universe. So the universe is shining at us with one of the most fundamental laws in physics. And here is a picture of the whole sky as measured by a later satellite. This satellite was named after Planck, given the great success of COBE measuring the Planck spectrum. And so this is the real sky in the universe. It's projected onto this ellipse, but actually this sky surrounds us. We live in the middle of it. And so as we look in all directions around us, this is what we would see if our eyes were sensitive to radio waves. And this satellite was designed exactly to measure these radio waves. And so what we're seeing here is a picture of the universe as it was roughly 14 billion years ago, just 400,000 years after the Big Bang. And these bumps in the radiation, so places where it's slightly hotter are a bit more red, where it's slightly colder are blue. And all these bumps really represent the variations in the temperature of the radiation as it came out from the Big Bang. And the temperature varied from place to place in the universe. And these variations were very, very important because the regions which were slightly more dense collapsed to form galaxies and stars and planets. The regions which were less dense expanded to become empty space in between the galaxies and the stars and the planets. And we are now able to take this picture of what we see directly as it was coming out of the Big Bang and to run time forward and to see how the galaxies formed and how the stars formed and compare predictions of based on physics with what we actually see around us in terms of galaxies and stars and planets and so on. So it's really very exciting that we're able to track the history of the universe over its entire lifetime of 14 billion years. This picture does not show us what happened before 400,000 years after the Big Bang. So the first 400,000 years, the universe was so dense, full of hot radiation, that light did not travel in straight lines through it. And so actually it is not transparent to light. And when we look back, we just see this hot plasma, like something like the surface of the sun. And we can't see into the sun because the sun is also opaque to light. But there are other ways in which we can look beyond this surface right back to the Big Bang itself. And those ways are very exciting, and I believe they will be made to work in the next 10, 20, or 30 years from now. I was very lucky that I started to work in cosmology when not everything had been properly interpreted. And so there was still work to do in understanding how the physical processes ended up making this pattern. So other people had calculated this graph. This graph shows the intensity of the radiation on the sky against the angular scale. Okay, so if I just go back to this picture, if I asked you to quantify this picture, you would say, well, there's a certain level of fluctuation on 1 degree. That would be a size roughly as big as this arrow is showing, 1 degree across. And then I could predict the amount of variation on 2 degrees, 5 degrees, 10 degrees, and so on. And that is what happens in this curve. So we see that as we go along the curve, we see different level of fluctuations. And actually, we understand this curve extremely well. It was also predicted long before the measurement. It was predicted in the 1970s by someone who recently won the Nobel Prize in physics for this prediction. And so here's the red curve is the prediction, the blue points are the measurements, and you can see they really agree very, very well. I was very lucky to get into this business of cosmology when nobody had calculated the polarization of the sky coming out of the Big Bang. And me and my colleagues calculated this red curve up here. And as you can see, the observations fit fantastically well with the theoretical prediction. And I emphasize the theory was done long before the observation was possible. So what do I conclude from these successes? What I conclude is that the universe is really strikingly simple. It obeys laws which we could discover long before we worked out all of their consequences. And when we work out those consequences, they agree very nicely with what we see. So this picture summarizes the large-scale universe, and the secrets of the universe are actually surprisingly few and surprisingly simple. The universe is not a complicated place. Very naively, you might have expected that the more we saw of the universe, the more complexity we would find. But in fact, the opposite is true. When we see the universe on bigger and bigger scales, it gets simpler and simpler. So in fact, the large-scale universe, the universe shown in this picture, seems to be characterized with just 5 basic numbers. One number is what's called the cosmological constant. This is the energy in empty space. If you had no atoms, no radiation, no anything, nevertheless, you would have some energy in plain empty space. And it's called the cosmological constant. It was anticipated by Einstein long before even it was understood that the universe is expanding. So it really is a very simple, mathematically simple postulate that there is a cosmological constant or energy of empty space. And so it seems to be there. And in fact, around 70% of all the energy we see in the universe takes this form. It's in this very simplest form of energy. Just a completely uniform, featureless, unchanging form of energy filling space. There's another form of energy called the dark matter. This is a different kind of energy. Like the cosmological constant, it does not shine, but it's very important in that it clumps gravitationally. And it was important in helping galaxies form under gravity. And we now have lots of evidence for dark matter. I'll show you a picture of the dark matter in a moment. And so we're pretty confident that it exists. And about 25% of the total energy in the universe is in this form of dark matter. And the last 5% is in matter with atomic nuclei, like us. We are made out of atoms. These are composed of atomic nuclei and electrons. And the Earth and the Sun and other planets and all the stars, these are made out of nuclear matter. And that comprises only 5% of the total energy in the universe. You also see in the picture these structures here. It looks like a spider's web coming out of the Big Bang. This is called the cosmic web. And basically these structures are what came out of these small variations in the density. And as you go forwards in time, i.e. the radiation emitted by the early universe was traveling towards us, we're going forwards in time, and we see how out of this web the galaxies and stars emerged, and ultimately the Earth and ourselves. So the early these early variations in the energy density have a certain strength, amplitude, and there's something called a tilt, which is a little bit technical. I can say more if you want later. But basically, there are only 5 numbers, and they characterize everything. And so far, we've gathered a lot of evidence, a lot of data, and everything we see is consistent with just these 5 numbers. So the universe is really amazingly simple. In a sense, it's as simple as something like, an atom or a molecule. It's much, much more simple than even a single bacteria. Just one bacteria is more complicated than the universe. You could not describe a bacteria with just one number, or with just 5 numbers, I should say. So the physical universe is really amazingly simple. Here's a picture of the cosmological constant, or the dark energy. It's very cheap to make this picture, but essentially this is what we learn from our telescopes, is that the dark energy fills space, and its most amazing property is that it repels gravitationally, whereas ordinary matter and dark matter attract gravitationally. So this dark energy is causing the universe to blow up in size, to get bigger and bigger. And if we ask what will happen in the future, this dark energy, will completely dominate. And the stuff we are made out of, the ordinary matter, will be diluted away to negligible level. So this is apparently our future, is dominated by this cosmological constant. Here's a nice picture, an old picture from the 1920s. And the person who solved Einstein's equation for the universe, was called Professor de Sitter. And here's de Sitter, and we call this cosmological constant lambda. This is a Greek letter, lambda. I said I would show you how we see the dark matter. We see the dark matter in the same way that you can see water in a glass. You see, water is transparent. It doesn't emit light. It doesn't reflect light, but it bends light. So if you look at a glass of water and you look at what's behind it, you can see there is water in the glass because the light gets distorted. And the same happens with the dark matter, is that we look at the background, which is the radiation coming out of the Big Bang, and as the light traveled from that background to us, it goes past this dark matter, and the dark matter bends the rays of light and distorts the pattern. And we can actually measure this distortion in what we see today. And from that, we can infer what the dark matter distribution looks like. So literally, we can see the dark matter through its effect in bending light. In this case, the light is the radio waves, which are the radio waves coming from the hot Big Bang to us. And so here's a telescope which measures these radio waves. It's in Chile, actually, at the top of a very tall mountain plateau called Atacama, the Atacama Desert. And here's literally a picture of the dark matter produced by this radio telescope. The picture here shows where the dark matter is more dense or less dense as we look out through it across the sky. So I think I want to stop there and ask if there are any questions. I'm just going to say that my own research tackles this very basic question of what happened. You see, here we see the universe coming out of a point, very hot, full of radiation, full of matter, these blue particles of matter. The hot surface we see that we saw from the Planck satellite, this hot surface is here at 400,000 years after the Big Bang. So time is going this way to the right. Time zero would be the Big Bang, this point, and then 400,000 years would be here when this radio waves were, what we see as radio waves now, was released. It travels to us, we live here. And you can see the universe now is blowing up due to the presence of the dark energy or the cosmological constant and its repulsive gravity. So this seems to be the history of the universe. We can study all of it using observations, using telescopes, and working out the consequences of the laws of physics. My own research is about what actually happened to start all of this off. So I think I want to ask for any questions or comments at this point. And please feel free to ask absolutely anything. There's no such thing as a silly question. I hope I gave you some impression of what cosmology is like.
Thank you very much, Professor Turok. Please do come in with some questions or just some comments if there is something that you don't understand or would like to say more about.
Yeah.
Did you want to say something?
Yes, Professor.
Please go ahead. Is that Abdullah?
This is
Yeah.
Yusuf.
Oh, Yusuf, go ahead, Yusuf. I will wait.
Oh, is it Yusuf? Sorry.
Okay, all right.
Good. Okay.
What I want to ask is about the Big Bang. I need to tell me the nuclear fusion reaction, the Big Bang, what causes the Big Bang to happen, and what are the nuclear fusion reaction inside the sun?
Good. So these questions are related, actually. So the nuclear fusion reactions in the sun are hydrogen, which is the simplest element. Hydrogen nucleus is just a proton with, it's a single particle. And hydrogen nuclei can fuse together to form helium. The helium nucleus has 4 nucleons, actually 2 protons, 2 neutrons. And when they fuse, when 4 atomic nuclei fuse to make helium, they release a lot of energy. So that's nuclear fusion. Now, in fact, I say they're the same thing because in the hot Big Bang, again, when the universe was very hot, it was all hydrogen. The mental picture you can have is that these protons and neutrons were just flying around free when the universe was very hot, because their attraction is too weak to bring them together. The temperature is so high, they just fly around freely. As the universe expands, it gets cooler, and what happens is the nuclear particles fuse. And when they fuse, that again releases energy. It heats the Big Bang a little bit, even more. It was already very hot, but it heats it a little bit when they fuse, and they form helium. And then, in fact, we are able to calculate, using the laws of physics, how much helium should form in the Big Bang, how much of the other elements, like lithium is another light element that was formed in the Big Bang, and deuterium is a sort of heavy form of hydrogen, also formed in the Big Bang. And those predictions also agree with observations. So right now in the universe, there's about 23%, most of it's hydrogen, most of the stuff in the universe. 77% is hydrogen, but 23% is helium. And then we have very small amounts of all the other elements. Most of the elements like oxygen, carbon, nitrogen, these were formed in stars after the Big Bang, and even heavier elements like iron and uranium. So to work out how much was produced later, you need to understand how stars work. But the light elements, hydrogen, helium, lithium, deuterium, those were actually formed in the hot Big Bang. And so this is, again, another piece of evidence in favor of this hot Big Bang picture. You asked about what caused the Big Bang, and that's an ancient question, okay, which even came before physics, right? What caused everything? My current belief is that that we need to change the question a little bit. I'm just going to show you, I'm going to jump ahead now because you've asked a question. My current picture of the Big Bang is as follows, that actually, let me just do this. Let me see. I'll use this picture. You see, this is the part of the Big Bang story which is more familiar. There was some event, and it runs forward in time going right. But actually, if you study the equations very carefully for the Big Bang, you discover that they allow, and in fact predict, a mirror Big Bang, literally a copy of the Big Bang, which goes in the other direction of time before the Big Bang. And what I now believe is that actually the Big Bang is a kind of mirror. And what happens at the Big Bang is more or less that the universe is reflected. So you know, if you have a mirror and you try to predict what you see in the mirror, of course the light comes off your face, bounces on the mirror, and comes back into your eye, right? So the mirror reflects the light. Now, one way to understand a mirror is to artificially create a copy of yourself behind the mirror, right? And if you are right-handed, you create a copy of yourself that is left-handed and put it behind the mirror, and then throw the mirror away, okay? And what you would see is a mirror image of yourself. And in physics, we call this the method of images. It's a way of solving a problem where the boundary condition, the condition at the mirror, is a particularly simple character. And that boundary condition is just sort of pure reflection. And so I believe the Big Bang is rather similar to that, that actually one way to understand the Big Bang is to make a copy of us, which is before the Big Bang. It's opposite in certain respects. The direction of time goes the other way. Our universe is full of matter. That's why this one is colored red. The universe, or this mirror universe before the Big Bang, is green. It's full of antimatter. It's another kind of matter which we know exists and which is really a kind of copy of the stuff we see. And so in this is a new picture of the Big Bang. This is what I have been developing over the last 10 years or so. And according to this picture, the Big Bang should not really be thought of as the origin of everything, just as you don't think of a mirror as the origin of your own image. The mirror is simply reflecting the light from you in it. The mirror is not adding anything. And in the same way, I think the Big Bang, my current understanding is the Big Bang is a kind of reflecting boundary to space and time. So it's a theory. And then, of course, the real test is, can you use that theory to predict some things and explain some things? And that's what we're busy doing. And so using this new picture, for example, we explained what the dark matter is. And we explained these fluctuations that you see in the sky, these ones here, right? We were able to explain these fluctuations and the dark matter with this scientific hypothesis that the Big Bang is a mirror. I hope that answered your question.
Yes, thank you, Professor.
Thank you.
I think there are questions from Abdul and also from Mir, if you are able to take those.
Sure. Abdul, please go ahead.
Thank you. I think Mia had a question before me. It's like in the chat. You will be able
Oh,
to
okay.
use that. My question is, well, might not be relevant, but I was looking back into the one of the slides, how you observed the
Okay.
polarization, and that was based on your research, how you come up with that calculation or the observation you've done of the polarization, the theory one, and then you said you have measured practically and you come up with that.
Right.
I have millions of questions, but some of them might be relevant always, like as I was following from the beginning to the end.
Sure.
Yeah.
Sure. Okay, let me answer Mary's question and then I'll come to yours.
Okay, thanks.
Okay, so Mary is asking, again, this is a question which everyone wants to know. Is there any evidence that aliens exist or that Earth has been visited by extraterrestrials? So, of course, it's a very, very fascinating question. So far, there is, I believe, no definite evidence for aliens, although people have really made a big effort to look for aliens. For example, there's a very big radio telescope in the US, which, well, actually what they do is they use the existing radio telescope, which was designed to do astronomy, but they examine the signal from that radio telescope all the time to try to find evidence for something like, transmission of a radio station. For example, if there was a voice pattern or some repeating signal, like a clock, they look for artificial signals in the radio waves. And they've spent a lot of money. I think right now it's getting up to at least $100 million, probably more, examining radio waves from the universe. And so far, all we see are the radio waves from the Big Bang which is just hot radiation. We see radio waves from stars, from things called neutron stars, which are pulsars, but these are not artificial objects. These are completely natural objects. So far we see absolutely no evidence for emissions from artificial beings like machines or people. And so it's strange. It seems that we are alone in the universe from the evidence we have so far. Or at least that life is of our kind is quite rare. Certainly, we are the only example of life that we know of. Has the Earth been visited by extraterrestrials? Again, people are really interested in this, and agencies like NASA in the US have spent large amounts of money trying to detect spaceships from from aliens. There are always claims, but so far not one of these claims has really held up to proper scrutiny. And usually, well, almost always when people have looked closer into these claims, it turns out there was just some confusion, and the evidence has not survived proper examination. So it is strange. One way of thinking about this is the way I like to think about the universe, is the universe seems to be extremely simple on small scales, right? When we look on small scales, we see atoms, we see particles, we see light. We don't see complicated structures on small scales. The best microscope we built is called the Large Hadron Collider, a very powerful microscope. But it just seems to be that matter is extremely simple at a basic level. Likewise, when we go to very, very large scales, the universe seems amazingly simple. We don't see artificial structures on large scale in the universe. It seems that the most complex things in the universe are actually us. We are the most complicated things we know of in the universe, right? A human being is extremely complex, and we cannot predict what humans will do, what they will do, either next month or in 100 years. We really have no idea what human beings may destroy the planet. That's one possibility. Or human beings may travel through space, and we may be able to visit other stars and other solar systems. And so in my optimistic moments, that's what I believe we will do. I'll tell you one very surprising fact, that I told you the universe is 14 billion years old, right? So light has taken 14 billion years to travel from the white surface to us, to be detected by our telescope. So 14 billion years. Now I can ask you, if we built a spaceship, how long would it take us to travel from where we are to the place where that light came from? Okay, so yeah, maybe let me just phrase that question. So it took light 14 billion years to get from the white, the place which emitted the white circle. It took 14 billion years from the light to get from there to us. How long would it take us to go from there to there, from here to there? Of course, it wouldn't be at that time. It would be at the future time, but at the same place in space that this Big Bang radiation came from. And so, and when I say how long would it take to travel, let's imagine we built a spaceship which I could travel comfortably in, okay, but which could accelerate as fast as possible and still have me living comfortably inside it. You know, how long would it take? Can anybody make a guess?
What it depends how fast with that space or whatever technology that we have.
So
I
that's
might
why, yeah. No, that's right.
sound
But
stupidly, but I don't know. That would be if it's traveling the same speed as the time.
yeah. So let me be a bit more careful. Um, if when I travel in a rocket, it has a certain G. We call it the G force. And so when a rocket accelerates, you are pressed against the floor of the rocket, right? And when people flying in planes do a sudden loop, they're accelerating and they experience what's called a many G force. It might be 10G and G is just the force we now feel on gravity, pulling us down in our seat or in the ground. That's 1G. So 10G, you can imagine, you're really pressed into your chair. And 100G, it becomes difficult to breathe. Okay, so let's imagine we built a spaceship which accelerates at 1G constantly. So it means it's getting faster and faster and faster and nearer to the speed of light all the time. But it's perfectly comfortable for us to sit in 1G. We would just feel like we're in normal gravity and, we'd move around inside the spaceship with this normal gravity. So a spaceship traveling at 1G, how long would it take us to go from Earth to the far reaches of the universe? And I don't expect you to get the answer right, because to get it right, you need to know relativity. And that's Einstein's theory, which basically blew everybody's mind in the early 20th century. And so Einstein completely revolutionized our ideas of space and time.
There is a suggested answer in the chat,
Oh, is there?
an estimate.
Oh, good. Trillion years. Okay. So no. The answer, amazingly, is 23 years. Okay. So you can say, how is that possible that I go from here to there, and there sounds at least 14 billion years away? How can I get there in 23 years? And the answer is that according to relativity, when you travel very, very close to the speed of light, you see, and even at 1G, you go up to almost the speed of light in about 1 year, right? You start off at 0, and then you go at 1G, which basically means, so 1G is 10 meters per second per second. It means you increase your speed by 10 meters per second every second. So after 1 second, I'm going 10 meters per second. After 2 seconds, 20 meters per second. 3 seconds, 30 meters per second. Okay, that's accelerating at 1G. So if you do that, according to relativity, when you travel very fast, space shrinks in the direction you're traveling. Space gets shorter. So I'm starting at Earth and I'm going off in this direction. And the faster I go, the more this distance shrinks. It literally becomes shorter and shorter. And after 23 years, I would reach the edge of the universe. And then, of course, I would have to slow down. Okay. So that would probably take another 23 years. Okay. To slow down at 1G in the opposite direction. And then I would be at the far edge of the universe. So again, what this tells me, it's a crazy thing, that this is possible. What it tells me is that for some reason, the universe is actually accessible to us. We, as I said, we seem to be the most complex things in the universe, and we seem to have the capacity to understand the universe and to build things which make use of the wonderful properties of the universe. Okay, and so in my optimistic moments, I believe that if only we can protect this special planet, look after it, and allow our civilization to grow, and education to spread, and science to progress, that we will be able to travel everywhere in the universe and explore all of its wonders. That is what the laws of physics tell us. That essentially all of this is possible. We don't know how to go backwards in time, but but we do know how to, in principle, how to explore the universe. And you can imagine the resources, the natural resources in the universe. For example, everywhere in the universe, all the time, are giant factories making gold, making diamonds, using nuclear fusion and creating energy like giant power stations. Even this dark matter is a form of energy which, in principle, could be used to drive spaceships. So there are unbelievable natural resources there. And it's within our future to make use of those. But the main question, of course, is whether we are sensible enough to look after the planet and to look after ourselves and to survive until this future time. Was there another? I think there was another question.
Abdul, did you ask your question?
I think I did ask about like I said, Professor Neil, I have millions of questions. Well, I won't say millions,
What's
but
the most
always
pressing?
questions. The one, how do you did the observation of or the graph you showed earlier, and
Yes.
is it because, I mean, how you?
Oh, how do you calculate it? Thank you.
Yeah, and
Yeah.
I have
No.
several questions, but I will leave it to that.
Right. So how do you get that graph? So as I said, it was getting this graph was the first graph was the most amazing one. This graph, right? And even the one before it. That was another graph. I showed you these two graphs, and in both cases, the theory was worked out before the experiment, long before. And then the experiment came along and it just fit beautifully. So let's start with this graph. How was this predicted? So Max Planck was a physicist working in Germany in around 1900. And he was actually given the task of understanding how to make light bulbs more efficient. Light bulb converts electrical energy, electricity, into light. But you want to use as little electricity as possible to make the maximum visible light, right? That would be the best light bulb. So Planck was given a contract. Tell me how to predict the radiation of a light bulb. And what he discovered is that the existing theory of radiation could not predict how much radiation would come from a light bulb. He had to actually invent a law, it's called Planck's law, which says that light comes in quanta, or packets of energy. And so he invented this law according to which light comes in packets. They're also called photons. They're like particles of light. He had to quantize the light in order to explain the radiation given off by electric light bulbs. When he did this, his theory of quanta, he then used to understand what would be the radiation from a hot body, a perfect hot body. and that's the green spectrum. He had no idea at the time that the universe would be shining with this spectrum, okay? And what he had in his mind was simply trying to explain how hot things like light bulbs shine. And so it's just amazing that he invented this quantum theory to solve a very particular problem. But it turned out that the same theory explains huge number of things in nature. I mean, the same quantum theory explains the spectra of atoms, for example, you know, how electrons orbit atomic nuclei. That was only understood with this quantum theory. So, yeah, these laws of physics come about in strange ways. Usually people do not follow a very logical route in getting there. But sometimes when you're lucky and you discover the right law, it turns out it describes the whole universe. I mean, much more than you expected. This other calculation here, the calculation of this pattern of radiation on the sky, the radio waves from the Big Bang, that really involves all of physics. There is what is called statistical physics. That's physics of hot matter. There's radiation physics. There's gravity. All of the physics you need to calculate this was basically developed by around 1920. Okay? And then later on, it wasn't until around 1960 that people began to believe there was a Big Bang and to work out in detail what the Big Bang would predict. And they just literally used all these laws of physics, statistical physics, radiation physics, gravitational physics, put them together, and this is the consequence. The curve is the consequence. So it's not easy to explain. You need essentially all of physics. But it's just amazing how these, you know, if you like, the best laws in physics, when put together, explain what we see in the universe in this amazingly precise way. In fact, so I was lucky. I just did a small step, which is to take the same kind of calculations and calculate this polarization. Now, if you look at the units of this curve, this is 70 microkelvin squared. What does that mean? Well, it's something squared. So, you know, the square root of 70 is about 8. And this is telling us that the polarization is about 8 microkelvin. Micro means 1 in a million. So it means that the light is polarized at 8 parts in 1 million. So it's very, very weak. This effect is extremely weak. You need really precise experiments to even detect it. And so when we first calculated this red curve, I went and talked to astronomers and I said, can you measure this? And they all said, no, it's too difficult. The signal is too weak for us to detect. And then 10 years later, they could detect it because their detectors had just become so accurate. So the one thing I learned is that we always underestimate what technology will do. And so even when you work on crazy theoretical ideas like what happened at the Big Bang, you know, it sounds absolutely untestable. But in fact, experimentalists are so clever and technology keeps advancing so fast that I now believe that within 20 or 30 years, we will actually be able to see, to literally see what happened at the Big Bang itself. And I may say a few more words about that if people want.
Can we just ask if anybody else here, like perhaps Ahmed or Farhad or Jonas, Ola would like to ask a question, just something that interests you, doesn't have to follow on from what came before. Would be good to hear.
And yes, and also if you just, express your feelings. I mean, uh, personally, I'm amazed that we can do that, and you can imagine that I enjoy working on this. It feels like a huge privilege to think about these issues. Um, what I want to convey is that it's not really a question of imposing my ideas or anyone else's ideas on the universe. It's much more a question of learning, of being open-minded and trying to see what we can learn, from nature directly. And the fact that we have learned so much, and it seems that we can learn much more, I find really exciting and interesting. It's something strange about our existence. Yeah, I can't explain it. Why should we be able to do this? It's crazy. But for that reason, I find it very fascinating. So even if you have a comment about, what you feel or what your opinion is, you don't have to ask a physics question. Uh, I'm very interested to share those feelings.
I have I don't know if it's a comment or feelings or a
Yeah,
question. I mean, because you started things very smoothly and explain how the education itself or exploration or all the known things have started in Africa. And
yes,
then all we hear is like explorers or people discovery has been made by Einstein,
right,
other
right.
explorers or people like what happened? Has it not been able for people like African, her background has not been able, or other nations to do the discoveries, or maybe we don't know, maybe those discoveries are there. The other question I have, Professor, sorry,
Great, great. No, that's a great question. Yeah,
is it possible that the humans, because of when you look at the pyramids or you look the existence of humans, how it started, is it possible that the humans were more intelligent before that we don't even know? Maybe it has been destroyed somehow,
yeah,
some point without traces.
yes.
And my other question is, sorry, my other question is, if you say we will be able to do that, will that be the you say we will be able to explore more in the future
Yes.
as humans. Is that because as humans or because of the support with what we nowadays call it AI, artificial intelligence, or other stuff, or
Yes.
and there are so many questions, like I said, but yeah, I'm just stopping there. I mean, I'm
Okay,
so
thank you. No, those are all great questions. Let me try and deal with the first one. How did this originate? How did this kind of knowledge originate? And why did it stop in Africa relative to Europe? Why did Europe take over and leave Africa far behind in the world of science? Um, So yeah, I just suggested and showed some examples of how mathematical science, and physics is a mathematical science, how it originated in Africa. There are other examples. For example, the first steam engine, right, which was, we always hear about the Industrial Revolution and the steam train invented in Britain. But actually, the first steam engine was in Egypt, in Alexandria. Somebody called Hero of Alexandria built a steam engine in, I think, 300 or 400 BC. Um, and it goes on. Okay, so there are many, many examples of mathematical understanding of nature, which came long before Europe, long before the Renaissance in Europe. Um, so the simple answer, I think, is that the this kind of knowledge in order to blossom, requires a sort of an environment in which people can think independently and develop their ideas. And for whatever reason, although many of the initial seeds were apparently born in Africa, they did not evolve into technologies. Okay, the pyramids, okay, it's one example of a big structure, but what was it for? It was for housing, the grave of a pharaoh. It wasn't for the benefit of the public. And so I'm afraid those inventions, and even the steam engine that was invented at that time, wasn't used to build railways, to build things that then spread, into public use. On the contrary, when Europe started to develop modern scientific ideas, and this really begins around 1600 with Galileo, the idea of modern science, of doing experiments, of comparing experiments with theory, mathematical theory. That begins with Galileo, as far as we know, in 1600. And of course the church tried to stop it. The Catholic Church was very unhappy with Galileo, and didn't like the idea that the Earth goes around the sun. They said the sun must go around the Earth, whereas actually Galileo was correct, that the Earth does go around the sun. So this in the Renaissance period in Europe, there was kind of sufficient wealth spread out, and there was sufficient openness to the development of new ideas that modern scientific thinking could really blossom. And we don't quite know why this didn't happen in Africa. One can guess it may have been partly historical accident, partly the social structure, or the way in which society was ruled in Africa. But once it arose, it led to all these technologies, guns, ships, being able to sail around the world, and of course the slave trade and the plunder of Africa for its raw materials, and colonialism, and so on. So essentially, because Europe got there first to the technological fruits of science, Africa was suppressed. And so it's no mystery that Africa was left far behind, because it was deliberately suppressed. What I see happening now is that Africa in particular, and many parts of the world, have a very young population. And they are all very aspiring. They want to progress, they want to advance. They're very interested in science. I would say more so than their Western counterparts. They're more determined. And when you talk about Einstein, you see, Einstein was not an insider. Einstein was a Jew. And Jews were not allowed to do science, physical science, until about 1850. Jews were all discriminated against, and it was felt that Jews were inferior and incapable of doing technical things like engineering or medicine. Jews should just be small traders. But then Einstein and some other Jews got into physics and maths, and after about 50 years, they absolutely revolutionized everything. And all the old physics was seen to be incomplete. And they developed the quantum theory. It was, many of the key people were Jewish. So I see the same possibility in the future that young Africans are going to get into science. It may take them 20 or 30 or 40 or 50 years to become the leaders, but when they do, they will change everything. So I'm actually very I think it's I see this already happening in China, for example. It's very obvious. I was just there last week. I was in China. There are lots of young people in China who now have excellent education, good standard of living, opportunities to do science, and they're coming very strongly, right? So already there are more scientific publications coming from China than from the US. And in 10 years' time, China will be well ahead of the US in science because it's educating its young people and investing in them and giving them opportunities. And I think the next such wave will be Africa, very likely. But it's very important to stabilize Africa and to, have wise governments who invest in young people and give them opportunity in order for this to happen. But Western civilization is relatively tired now. You can see it in all kinds of ways, right? We see Donald Trump as the leading candidate in the US. I mean, that is not the choice of an intelligent population, right? And so, so I think the future of continents like Africa is actually crucial. And I hope that those young people, when they do get a chance to be educated and develop and do science and technology and engineering, that they will be, will be wiser than their Western counterparts.
Thank you. Can we see if there, I think Abdul may still have some unanswered questions, but I'm just wondering if anybody else here would also like to.
Excuse me, Karin, can I ask a question of Professor?
Of course, please go ahead.
Yeah, thank you, Professor, for explanation about the area of question of us. And so, how do you predict of the future of the sun?
The sun. Okay.
Yes.
So yeah, we can. It's amazing that the same laws of physics can be used to predict the evolution of stars, and this is now something that is really very well understood. So you can look at a given star, you can see how much mass it has, what is its temperature, and just follow the future evolutions. So we know. And then we have lots of observations now. So lots of telescopes are observing stars all the time and checking these predictions. So in the case of our own sun, we know that in a few billion years, I forget the exact number, but it's I think maximum 10 billion years, probably less than that, a few billion years, our own sun will run out of nuclear energy. That's because the hydrogen which fuses into helium, that's the source of energy in the sun, the hydrogen will run out. It will just run out of hydrogen, have lots of helium, but not much hydrogen left. And slowly the sun will get colder. It will go from being yellow to being red. And then because as this happens, as it becomes redder and redder, actually its size will swell. It becomes what's called a red giant. And so we can see stars like this currently elsewhere in the universe. The size will grow, and eventually the sun will grow large enough to actually encompass the Earth itself, right? So the Earth is orbiting at a certain distance from the sun, but if the sun really grows big enough, then the Earth will find itself traveling through the outer edges of the sun, and that won't be very good for life. because it will be way too hot for people like us to survive. So we think that unfortunately the future of this particular planet in several billion years will be to become uninhabitable. So that's actually another reason why we need to develop the capability to travel somewhere else. We can't stay here forever. But this is a very long time scale. I mean, I'm more worried about the short term. We need to protect this Earth for at least the next 1 million years. If the Earth ultimately is destroyed in 1 billion years' time, that I don't think that'll be a problem. By that time, we will easily be able to travel to another planet.
Excuse me, Professor. Can I ask a question again?
Sure.
About the project of Starlink company about traveling the humankind to the Mars.
Right.
It is correct right now or not? It is just for the ambition project about the other things about the U.S. governments. What do you think about that?
Sorry, I didn't quite understand. So you want to ask about the program to put a human on Mars?
Yes, by
And
the Starlink company.
by Starlink? Oh, by
Yes.
Elon Musk.
Yes, Elon Musk.
Yeah, so
Yeah, because you mentioned to the Trump and so the China, but I
right.
think it's the Trump is trying for fight about the democracy, and so I think
Right.
I believe to him, and so
Right.
that's important. Yeah.
So actually, I was fortunate to have dinner once with Elon Musk in his SpaceX company in Los Angeles, and he kindly gave me dinner there, and I walked around the factory where they make SpaceX rocket ships, and of course, it's very impressive. He's a very, very good engineer, and he's already done amazing things. But you have to understand that being technically gifted and capable doesn't always come with great wisdom. Okay. And the way I see him acting now, it's very impressive, but sometimes quite unwise. In particular, the way he's been managing Twitter seems really stupid to me. But are we? So I think his company will be capable of traveling to Mars. There doesn't seem to be any technical obstacle, and the U.S. government can easily pay for that. Surviving on Mars will be extremely difficult. There's no atmosphere, so that you can't breathe. So I don't think that's a place we want to move to. Um, but in terms of just developing the capability of traveling large distances in the universe, that's an important step. At the moment, I don't see it as a huge priority. I mean, to me, it's much more important to look after this planet. And I wish Elon Musk would devote more of his resources on technologies which, monitor the health of our planet and identify sources of pollution and destruction and carbon emission and so on, because that's a much more urgent priority. So it worries me that the very rich people like Elon Musk and Jeff Bezos of Amazon, these guys want to spend their money on spaceships, which could maybe save them if the Earth is no longer habitable. It could save a few of them, but I think that's really very short-term thinking. I mean, they won't live much of a life if it's just them who is saved. So these very, very rich people, I'm afraid, are not necessarily very wise.
Thank you.
Usually it's the opposite. You find poorer people are more wise than rich people.
Thank you. I'm just wondering if we could hear from some of the people who haven't yet spoken. I think Ahmed is still here, and Ola.
Hello, this is Jonas.
Hi,
Jonas.
Jonas.
Yes, hi.
Yeah, thank you, Professor. I have two questions. The first one is, what's the time frame that for theoretical physics to be proven by experimental physics? Is there a time frame? We can
Yes.
explain it in your research also.
Yes.
My second question is there any other research which challenges the Big Bang theory, proven or disproven? Any ongoing research?
Yes.
I want to ask you about these questions. Thank you.
Okay, thank you. So in terms of the time frame, it depends on the detail. So in particular, me and my colleagues have a proposal for explaining the dark matter. I mentioned it briefly. And that proposal can be tested in the next 5 years. So I think in my to be optimistic, I would say that I would hope that in 5 years' time we will be pretty sure what the dark matter is. Okay, that would be great progress if we can understand that. If we, in terms of understanding what happened at the Big Bang, you see, you always have to have a combination of a good theory, which is logical, clear, the mathematics makes sense. You need that theory, and you need an experiment which will confirm that the theory's predictions are correct. So in developing the theory, I would say the timescale is probably 10 years. I'm hopeful. Again, that's an optimistic prediction, but it could be that in 10 years from now, we really have a good theory of the Big Bang as a mirror. The experiment, there is one experiment which could be done to verify that theory, and that is the detection of gravitational waves. We have already seen gravitational waves from coming about from the merger of black holes. You know, we see black holes in the universe, and when you have two black holes, they orbit each other, and they, as they're going round and around, they're emitting gravitational waves, and those were detected about 5 years ago. It's a spectacular experiment and agrees perfectly with Einstein's theory of gravity. So we can detect gravitational waves. In principle, we can use gravitational waves to see right through the Big Bang to the initial point. Because this hot plasma in the early universe, although light can't travel through it, gravitational waves can travel freely through it. They're just like a kind of X-ray. Just like you can look into your body with an X-ray or ultrasound, we could use gravitational waves to look into the Big Bang and see what happened in the beginning. So right now there are a number of experimental teams that are developing the technology. It's extremely difficult experiment. And so I don't think we will be there for 20 or 30 years. But in 20 or 30 years' time, I'm hopeful that we'll actually have the capability of seeing what happened at the Big Bang itself. That's very exciting. And then you had a second question. I've forgotten it now. Sorry.
Yeah, is there any ongoing alternative
Oh,
theory
yes,
which
to the Big
challenges the
Bang.
Big Bang theory? Yeah.
You know, honestly, I could say, so I was actually very fortunate to be in the audience when that first green curve was confirmed. You know, Kobe, 1992, that curve, the red crosses on top of the green curve, that was first revealed in a scientific seminar in the US, in Princeton, in 90, I think it was, yeah, either 92 or 93. And I was in the audience. And as soon as that curve was shown, people said, okay, the Big Bang really happened. I mean, this is just a perfect agreement. This is very, very rare in science that you get such a accurate prediction. And so I think, 99.99% of cosmologists accept the Big Bang. Not because we're believers, but because we see the evidence. And by now there's so much of it. Still, there is maybe 0.001% of people who are trying alternatives. There's a theory called the steady state theory, which actually very good physicists developed in the 1960s. But every new piece of evidence goes against that theory. And so it's really a big struggle to try to have that theory survive. So I would say at the moment, the vast majority of people who work on this kind of subject accept the Big Bang. Now, actually, I myself am in a small minority. There is a standard view of the Big Bang called the theory of inflation. I don't know if you've heard of it, but if you look online, there's this theory called cosmic inflation. It's like economic inflation, but it's the inflation of the cosmos. And this theory is believed by the majority of cosmologists as explaining the Big Bang. They don't. So most people do not believe my mirror theory yet. They mostly believe this older theory. It's 40 years old and called inflation. And I'm a critic of that theory. And so there is a lot of competition between theories. Ultimately, what resolves the competition is that experiments come along and check the predictions of the theory. And if they disagree, then the theory is abandoned. And I believe that's what will happen with the theory of inflation. It makes certain predictions, which now the experiments are checking, and the better they check, the worse the theory looks. So theories do go out of fashion. And it's possible that the Big Bang Theory, let's say 100 years from now, somebody will do an experiment and they'll find something which is, the universe is supposed to be 14 billion years old, according to the Big Bang Theory. If we discover one object that is 15 billion years old, then the Big Bang Theory is disproved. And so sometimes in the media, you will see reports, oh, very old galaxy discovered, and this disproves the Big Bang. You often see reports like that. But when you look in detail at exactly what they found, unfortunately, this evidence doesn't usually last long. Usually it turns out they made a mistake in one way or the other. So yeah, but the theory is very easy in principle to prove wrong. You just need to see one object that is more than 14 billion years old, and then Big Bang Theory would be finished. So, but I think there's so much evidence now that I doubt that will happen, at least not soon.
Thank you.
Thank you. I think there are still a couple of people. I don't want to keep Professor Turok too long, but if there are people who still haven't asked a question, I think that would be Ahmed and Abdullahi Farah, maybe, unless you asked a question. I'm not sure. Would anybody else like to comment or describe what your reactions to all this amazing information and theory that we are hearing about tonight?
I think the professor explained very delicately and very extensive. So yeah, I think we have benefits his time and I mean, we could stay here all night if, yeah,
Thank you. You're very kind.
yeah, definitely. So there was this I was thinking about one, and it's not a question, Professor, but if like on that circle is an outer circle, you said, and then
Mm,
we have these our solar system and the other galaxies
mm,
scattered all over the place. I mean, I was
mm.
wondering where does like our own galaxy stands, um and and then
Yeah, it's
I was
another.
another question, but where do we do? Well, let me just stop there because I will.
Sure. That's another great question. Okay, so here's the picture.
Yeah.
Now, as I mentioned, this picture is a bit weird to get your head around. Okay, we are here in the middle of this picture. Here is the solar system. The edge of the picture is the Big Bang itself. And as I mentioned, it looks like it's very large in the picture. It looks like it's the largest thing, but actually it's the smallest thing, okay? Because you see, what the picture really shows is what light would experience in traveling from the Big Bang to us. So you should think about this picture at the same time as thinking about this other picture. Let's see, this picture, right? So here's the Big Bang. And if I follow light from the Big Bang to us, it travels. There are two things. It's coming towards us, but the region it is coming from is expanding. Okay, this picture shows how the Big Bang expands into a bigger and bigger universe over time. So if I go back here, let's go back to this one. Yeah. So actually, when you look at this picture, it's kind of a snapshot going backwards in time, but where we try to represent the earliest objects as being furthest from us. Okay? So the picture doesn't properly show that the universe was shrinking in size as we went back in time. So you have to keep that in mind, is that these things are actually hard to make a good picture of. Now, the other thing to say is this picture it looks like the different regions of space are all different, right? So here we are in a solar system that's inside a galaxy, that's this cloudy thing, the Milky Way, surrounded by other galaxies, surrounded by this web and the red circle and then the white circle. But in fact, according to the theory of the Big Bang, everywhere in space undergoes an almost identical history. Okay? So we are not in a special place. We are not in the center of the universe. It's just that we are the oldest thing we see. Because as we look outwards, we're seeing the universe as it was longer and longer ago. You know, if I look out 1 billion light years, I'm seeing stars as they were 1 billion years ago. When I look out 10 billion light years, which may be here, I'm just seeing the universe, this region of the universe, as it was just forming galaxies. So it's a long time ago, right? So it's more like what we're seeing is a historical record. You know, if we look through rocks, if you see a cliff, the layers of rock were formed longer and longer ago. As you go deeper into the rock, the layers were older and older, and so you may find a dinosaur in the very deep layers. Okay, and so this picture is more or less like the layers in the universe the oldest layer would be this white circle, then the red circle, then we see galaxies forming and so on. So yeah, as I say, these pictures are not perfect representations of the evolution of the universe. They're really just pictures of what we can see.
Thank you. I feel like we should probably wind this up now because Professor Turok spent a long time, actually quite a lot longer than we predicted.
It's my pleasure. Thank you for
Proving the theory of seminars in a dramatic way. So thank you very much. I think we're all very grateful for you for spending time on this. And for those of any of people who you may know that weren't able to come, we're going to make this available. Professor Turok's kindly said we can make it available as a freely available
of course.
recording online.
Okay, may I just wish you, all of you, success in your, I know you're going through struggles to get a better life and to settle in the UK, hopefully, and I'm sure many of you are trying to bring family and support relatives elsewhere, and I just wish you all strength and all courage in facing up to that. And you know, I would be delighted to come back to you and talk to you at some point in the future. So yeah, hope one day we will meet. And thank you for your excellent questions.
Thank you so much. I agree. Very good questions, everyone. Thank you and have a good holiday.
Thank you. Take care.
Good night, everyone.
Good night.